Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss thermodynamic potentials and their applications. Let's begin. What is thermodynamic potentials? Basically, we know the thermodynamic variables as pressure, volume, temperature. These are the thermodynamic variables. These thermodynamic variables are used to describe the thermodynamic property of the system. Means, knowing these thermodynamic coordinates, we can easily study the law that govern the conversion of energy from one form to another, and we can obtain the direction in which heat will flow, and we can also study the availability of energy to do work. And due to combining these thermodynamic variables, and additional information concerning the thermodynamic system can be obtained by defining such thermodynamic variables, which is known as thermodynamic potentials. Thermodynamic potentials means combining these thermodynamic variables, we get another term which is known as the thermodynamic potentials. With the help of these thermodynamic potentials, we get an additional information concerning to that of thermodynamic system. Okay, and we define that thermodynamic potential. Thermodynamic potential is a scalar function and used to represent the thermodynamic state of a system. That represent the thermodynamic state of a system. These are known as the thermodynamic potentials. There are 4 thermodynamic potentials we have to study in this video. One is internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Let's discuss one by one thermodynamic potentials, their properties and applications. So, first one, that is internal energy, which is represented by the symbol U. Internal energy basically defined as the total energy of a system. Total energy in the sense that is the sum of kinetic and potential energy of the atoms, or we can say the molecules that are present in that of system, and that can be transformed directly to heat. And we get the mathematical form of that internal energy from first law of thermodynamics. Let dq amount of heat is supplied to that of system, then that amount of heat is used to change in internal energy plus some work done. Now here in place of a dq, I can use T ds, that from second law of thermodynamics, the value of dq, T be the temperature, ds is the change in entropy, and du again in place of dw, that is P dV, or du is equal to T ds minus P dV. du is equal to T ds minus P dV. Look at that particular equation here. That means internal energy depend upon change in entropy and change in volume. Change in entropy and change in volume. That's why here we write U. So U is a function of S, entropy, and volume V. U is a function of entropy and volume. U is a function of two variables, entropy and volume, so that the above equation can have two partial differential equations. Let I define here. When treating as V as constant, when volume will be constant, that means that term will be 0, only du is equal to TdS. So T is equal to du by ds at constant volume. So here the first partial differential equation, that is del u by del s, whereas volume as constant, V as constant. When V constant, that term will be 0, only that term exists. So T is equal to du by ds at constant volume, that is the temperature. And again, when S be constant, so change in entropy will be 0, therefore du is equal to minus P dV, and du by dV is equal to minus P. So del u by del V, whereas S is equal to constant, is equal to minus P. These two equations, partial differential equations, is derived from the internal energy concept. Okay, U is a function of S and V, so del U by del S, V constant is equal to T, del U by del V, S constant is equal to minus P. From that equation, du is equal to TdS minus P dV. So this is the basics of internal energy, which is one of the thermodynamic potential. Another thermodynamic potential, which is the enthalpy. Enthalpy, that is denoted by H. The enthalpy S of a system is defined as the thermodynamic property of the system that can be described as S is equal to U plus PV. And enthalpy, the change in enthalpy is a measure of heat evolved or absorbed during a process at constant temperature. So enthalpy means the heat content of that of system, how much amount of heat absorbed or how much amount of heat released, that can be studied with the concept of enthalpy. So enthalpy is given as S is equal to U plus PV. Now differentiating, here is the enthalpy. And now differentiating, we get, look at the terms like ds. Previously we discussed du. These terms are exact differentiable. exact differentiable in the sense any function which is independent of the particular path and depends upon the initial and final position. This type of change in that function denotes as the partial differential, or which is also known as the exact differential or total differentials. So these functions ds, du are exact differentials, that is why we take TDS, PdV. Now here S with the exact differential, that is why dH is equal to du plus, that is PdV plus VdP, 2 are multiplied, PdV plus VdP is equal to du plus PdV, that is dq according to first law of thermodynamics, dq plus VdP. Now dq is equal to TdS from the second law of thermodynamics plus VdP. Your dH is equal to that much, or dH is equal to that much. Look at that particular equation. S is a function of S and P, that means change in S and change in P, change in entropy and change in pressure. So enthalpy H is a function of S and P. Again we have two partial differentials here. When S is constant, so change in entropy will be 0, that means dH is equal to VdP and V is equal to ds by dP at constant entropy. And again when P is constant, that term will be 0, so T is equal to ds by ds at constant pressure. Therefore we have two partial differentials, that is del S by del S at constant pressure, it will be temperature, and del H by del P at constant S as constant, here entropy as constant, is known as volume. So that is the expression partial differentials from that equation of enthalpy. This is enthalpy. Next, another thermodynamic potential, Helmholtz free energy. Helmholtz free energy, which is denoted by F. Helmholtz free energy is the thermodynamic property of the system and which is defined as F is equal to U minus ds. That means it is the measure of the ability of a system to do useful work, to do useful non-mechanical work plus mechanical work. That is the combination of non-mechanical plus mechanical work. What is non-mechanical or mechanical work? Let me take an example. Let that is a piston. There will be the gas molecules. That expansion of gases means the piston up, and the compression of gases means the piston down. This type of work is known as mechanical work. That type of work is the mechanical mechanical work, which is basically known as the PV work, pressure volume work. Let I take another type of work, but that is due to the flow of charge. Let I take the chemical reaction in case of a battery. In case of that battery, the chemical reactions are carried out through that of cell or the battery. In that type of work is known as non-mechanical work. Non-mechanical work, or we can say that is the non-PV work. Non-PV work. There will be no such existence of pressure and volume. So this way we define mechanical work and non-mechanical work. Here Gibbs free energy, that is the Helmholtz free energy, is the ability of the system to do useful of mechanical work plus non-mechanical work. So how we mathematically define that one? So Helmholtz free energy, Helmholtz free energy, F is equal to U minus Ts. Now differentiating both sides, we get that is df, which is exact differentials. Df is equal to du minus that is Tds, that is derivative of Ts, is equal to du minus that is T ds minus S dt. Derivative of first term, second term T as constant, and derivative of second term, first term T as constant. Here in place of T ds, that is dq, du minus dq S dt. Now in place of dq I write that is du plus pdv, so minus du minus pdv minus S dt. Du cancel out, we have minus pdv minus S dt. So in place of pdv we substitute that the work done, that is minus dw minus S dt. Or just we can write here, just write that one. That equation is sufficient to describe its differentials. df is equal to minus pdv minus S dt. So what f is a function of that change in volume and change in temperature, volume and temperature. Now using that particular equation I can derive two partial differentials. The partial differentials look like this. When volume is constant, that is df is equal to minus STT, and df by dt is equal to minus S, and again when temperature is constant, that term vanishes, therefore df is equal to minus pdv and df by dv is equal to minus p. So I write two differentials here. The differentials look like this: del f del v at t is equal to constant equal to minus p, and del f by del t at V is equal to constant at minus S. These are the two partial differentials from this equation of Helmholtz free energy. This is Helmholtz free energy. Next, another thermodynamic potential which is known as Gibbs free energy, that is denoted by capital letter G. Gibbs function, also referred as the Gibbs free energy, which is the thermodynamic property of the system and is defined as G is equal to S minus Ts. And Gibbs energy of a system is defined as the maximum amount of energy available to a system during a process that can be converted into useful work, and that work which is converted, that is the measure of capacity to do useful non-mechanical work. Here notice that is the measure of capacity to do useful non-mechanical work. In case of Helmholtz free energy, that is the mechanical work plus non-mechanical work, the capacity of to do useful mechanical work plus non-mechanical work. But here in case of Gibbs free energy, that the capacity to do useful non-mechanical work, non-mechanical in the sense in case of like cell or the work that is done in case of the flow of charge, that type of work is also known as non-PV work, which is non-mechanical work. So that is the measure of capacity of do useful non-mechanical work is the Gibbs free energy. Mathematically we can say the Gibbs free energy Gibbs free energy that is G is equal to S minus Ts. So in place of S I substitute, that is U plus PV. So U plus PV minus Ts. G is equal to that much. Now differentiating both sides, and differentiating what we get, dg is equal to du plus pdv plus vdp minus tds minus sdt. Here the multiplication of two term, that is the multiplication of two term, since that is the exact differential. So derivative of first term, second term as constant, plus derivative of second term, first term t as constant. Again derivative of second term, first term t as constant, derivative of second term, first term t as constant. That is the multiplication rule of differentiation is used here. Now dg is equal to du plus pdv, that is dq plus vdp minus, in place of tds, that is dq sdt. Okay, dq cancel out, or dg is equal to vdp minus sdt. Look at that equation. So G is a function of change in pressure and change in temperature, that is P and T, pressure and temperature. So Gibbs free energy is a function of pressure and temperature. Again here also we get two partial differentials by using pressure as constant and temperature as constant. So what we have? We have del G del P at T is equal to constant, we have V, and del G del T P as constant, that is minus S. Two partial differentials from Gibbs free energy. So this is all about Gibbs free energy, its property and the partial differentials. So what we studied throughout the entire video lecture, we studied here what is thermodynamic potentials, why it is necessary to study about thermodynamic potentials. So there are 4 thermodynamic potentials that we have to discuss elaborately in this chapter. One is internal energy, that is the function of entropy and volume. Here are the partial differentials. Again enthalpy, which is the function of entropy and pressure, then its partial differentials. Again Helmholtz free energy, which is the function of volume and temperature, again its 2 partial differentials. And Gibbs free energy, which is the function of pressure and temperature and its 2 partial differentials. So with this useful and informative notes, let me wind up this session. Thank you.